shall now look at the SPICE simulation of the hill climbing method of maximum power point tracking. We will use this algorithm. We will use all these blocks. We will measure the current, measure the voltage, calculate the power, pass it through a slow filter and a fast filter, comparator, toggle flip-flop, filter, and then PWM, and then giving it to the duty cycle input of a DC-DC converter. The DC-DC converter we will choose is the buck boost converter because it is able to operate on the entire IV characteristic. So let us go to SPICE and see how we will be able to simulate all this block and integrate it with the operation of the buck boost converter interfaced with the PV source. So in the simulation folder, I have one folder called PV MPPT. Within that folder, you will see that there is a MPPT schematic, the subcircuit, PV subcircuit file with added components. I will show you what the added components are, and then of course the mppt.cir file. Let us open the schematic file and let me zoom in. Observe here that this schematic is linked to pv.subcircuit. Now this schematic here we are familiar with. This is the PV source. This is the power semiconductor switch L and the diode. This is a buck boost converter which is having V0 is equal to Vin or Vt into d by 1 minus d. The difference here is in these blocks which are ultimately generating the proper duty cycle signal for switching this IGBT. Now how are these blocks functioning and do they agree with what we had discussed earlier? So let me put up the set of block diagram that we had discussed while discussing the hill climbing algorithm, and let us compare and try to understand this. So here at the bottom part of the screen we see the block diagram that we drew while discussing the hill climbing method, and on the top part of the screen I am having the GEDS schematic editor in which I have included these set of block diagrams to generate the duty cycle for the buck boost converter which is interfacing the PV source. Observe here in the block diagram that we discussed, IT and VT are measured, sensed and passed to a multiplier to obtain P. Here also the voltage of this node VT is the terminal voltage of the PV source, and B sense is sensing the current of the PV source, which is the current flowing through the VIPV source, which is set to a value 0. So B sense is basically a sense where it is giving an output voltage proportional to IVIPV. So it is basically giving a voltage proportional to the current flowing through the PV cell or the PV module. I am using a multiplier here. Now this multiplier multiplies VT and IPV and gives you the power output of the panel. This multiplier block is a new block. You see that NgSpice integrates very nicely with CEDAR and NgSpice. NgSpice and CEDAR tools, CEDAR libraries are also integrated well within NgSpice. These set of blocks here are analog behavioral modeling blocks, and they are obtained from the NgSpice library. It is available in NgSpice. It is well integrated and available in NgSpice. I will tell you how this can be made, or how the subcircuit for this is, and I will share with you the symbols and the subcircuits. So output of the multiplier gives the power. Now the power is passed through two filters. One is called the slow filter and another is called the fast filter to obtain P base and P current. Now here also I am going to pass it through two first order filters. Power is passed through a first order filter. I will call that one as the slow filter, and you will get PB to represent P base. And the same power is passed through another first order filter, the different time constant. I'll call it fast filter, and I'll say PD, P dynamic. So within the filter, if you see the value here, it is calling the subcircuit filt underscore order underscore 1. It's a first order. K, gain of the filter, is 1, and A, which is the time constant, it is of the form 1 by AS plus 1, where A is the time constant. I am setting it at 100 milliseconds. So this is the slow filter. The fast filter is much faster with a very low time constant. So I am setting the time constant value to 1 millisecond. So therefore this is the fast filter. So output of this slow and fast filters goes through a comparator, plus minus, and output of that goes through a toggle flip-flop. Here also in the schematic, you have the plus minus goes through a sigma block. The output of the sigma block is analog in nature, but I have not put a comparator here because the toggle flip-flop here inside the input is containing a Schmidt comparator. Therefore, I can directly give an analog signal to that. The output of the toggle flip-flop, I will tell you why this is later. Output of the toggle flip-flop goes through a gain block, a summing block, and then a filter. In this block diagram, we are giving the output of the toggle flip-flop to a filter and then to the PWM. See, in the PWM that we are using, the triangle carrier is swinging from -1 to +1. Therefore, the voltage here should swing from -1 to +1. -1 should represent 0 and +1 should represent 1. And therefore, this gain block. Remember that the toggle flip-flop is going to give an output from 0 to 1. I multiply by a gain of 2. The output of this has a value from 0 to 2. I am now subtracting 1 from this, so it becomes -1 to +1. That's what is given to the input of the filter, and the output of the filter can swing from at most -1 to +1 limits, which goes to the PWM and goes to the duty cycle input of the buck boost converter. Now, VSET here. Why have I given this VSET? This is given to the S and R asynchronous inputs of the toggle flip-flop. At the time of switch on, we don't know what will be the output state of the toggle flip-flop. In order to be consistent, it is normal to give to the set input a small monoshot, which will give a high here momentarily, set this, and then from there on the tracking continues. So that is basically what I have done. I have given a very small, a monoshot type of a signal. I have used the piecewise linear. At 0 it is 1, after 1 microseconds it is 1, after 2 microseconds it is 0, and after 1000 microseconds, 1000 milliseconds, 1 second, it is still continuing to 0. So it's a very small pulse which I give to initially set Q to a high state, and from there on the closed loop will take over. So that is why this portion is come into picture, and we offset here of 1. I just explained to you in order to get here plus and minus limits for the PWM signal input. So here you see that there are so many new blocks. One is the multiplier, I already told you. This first order filter, this is also a new block. These two, 1, 2 and 3, all first order filters have the same subcircuit. There is a sigma block, summer block, plus and minus. There is a toggle flip-flop. How do we do a toggle flip-flop? There is a gain block. Okay, this PWM block we have already seen earlier. So these are all based on analog behavioral modeling, and they can be easily included as subcircuits in NgSpice. Now I will open this pv.sub file and let us have a look at the subcircuit inside it. Let me keep it to one side. Okay. Now look at this multiplier block here. So this multiplier block is given here. Subcircuit multiplier block, node 1, node 2, output node. So that is what this is. And all analog behavioral modeling starts with letter A. Okay, and I'm giving the inputs as a vector, output, and then I'm giving a model name, and in the model I have the mult as the multiplier model which will come in. You can refer to the NgSpice manual to get the idea of the syntax of this. So I have the multiplier model here. I have the gain model. You see that I use gain. I have the gain model here. The flip-flop, I have the summer block. The model of the summer block is here. Flip-flop block, the model for flip-flop is given here. See subcircuit, toggle flip-flop. The inputs clock, then Q, output, asynchronous set, asynchronous reset. So you see there is a Schmidt. All the inputs are passed through a Schmidt comparator. The Schmidt comparator model is kept here. And after passing through the Schmidt comparator, they are passed through an analog buffer. It's an ADC bridge. Every analog signal has to be passed through an ADC bridge before it is put into the digital domain. So in any mixed mode simulation, keep this very important thing in mind. Any analog signal, pass it through an ADC bridge, take it into the digital domain, and do the digital domain operation here. Model of the toggle flip-flop is D_TFF. Look into NgSpice manual for syntax. And then after doing the digital, you bring it out into the analog world by using a DAC buffer, that is a DAC bridge. So analog to digital conversion is by the ADC bridge, and all the digital work is done, and then it is brought back into the analog world by the DAC bridge. These two operations are very important in any mixed mode signal analysis in SPICE. Okay, so you have the toggle flip-flop, and we can also have a look at the filter. You see this filter 1, 2 and 3 filters are here. I have a first order filter. It's very simple in implementation. Subcircuit first order, filter order 1, input node, output node, gain of 1 and a time constant, default 1. So this is the model of the filter S_X FER, gain, the integral initial conditions 0, 0, numerator coefficient 1, denominator coefficient a and 1. So it is 1 by as plus 1. This is basically from the right increasing order of the powers of s to the power of 0, s to the power of 1, like that. So in this way, first order filter is done. And the symbols for that, like before, I have already done that and kept, and then called it from within the symbol files. So you will see that when I open this block in the A block directory, I have, see, the filter symbol. I have the symbol for toggle flip-flop. I have the symbol for summing, and symbol for multiplying. So like that, the symbol, I made the symbol and placed it in the proper place. I will share them with you so that you can also work on it and then make the simulation work. So now we will go to performing this simulation. So what is it? This is existing, which we had done before up to this point. We had done before. We are now going to give this in a closed loop way, sensing the voltage and the current. And we expect that whatever may be or not, this will always go and adjust the value of the duty cycle in such a way that maximum power is drawn from the PV source. Now that is what we want to see. So first we will set this at 100 ohms and see that it will go and settle at some duty cycle providing maximum power, and then we will change R0 and then see that it will settle at a new value of duty cycle also providing the same maximum power. Now that would complete our experiment. Remember that this is a closed loop operation now. This filter time constant, this filter time constant, this filter time constant need to be properly tuned if you have to get good results. I have just done a draft tuning, which is a rough tuning, and you will see that the PPT is tracking, but I will leave it to you to do a fine tuning and see if you can get better results. Now let us go back to the terminal and simulate in NgSpice. So I will use gnetlist generate mppt.net from the schematic. We will do that. So the net file is generated, and now I will type NgSpice mppt.car. I have given 1000 milliseconds as the total time, and it will take some time, but we will run this. So it will run for some time, few minutes. Let me come back in a few minutes. So the simulation is now about to complete, and it has completed. Now we can plot and see what is the duty cycle value here. The node for that is Vg. We can plot Vg and see. Now that would be switched pulses. Instead I will plot Vd here, which is the DC input to the PWM. So plot V of D. So if I expand that, so observe that the duty cycle starts from 0 and then picks up and tries to oscillate and stabilize around the maximum power point, operating point. So you see that I said that it should settle at around 0.56 or so. So this is settling at around that value. So you see that maximum power point tracking is happening. It is tracking the max power. We could also sense plot Vt. We will now plot terminal voltage into PV current, PIPV. So this is the power that is drawn from the PV panel. So you see here again that the power gradually hovers and then finally settles at the around the 26 watt value, which is the peak power point of the PV source. So you see that the maximum power point tracking is happening by this algorithm, by this hill climbing algorithm. What we shall now do is change the value of R0 from 100 to some other value. Let us choose now R0 of 70. So for R0 of 70, the corresponding duty cycle is 0.75, which will work out to be 0.75 into 2 minus 1, around 0.5 will be the value of the voltage input to the PWM carrier. So let us see if we alter the R0 value to 70 and then resimulate, the duty cycle will settle down with new value, yet still giving peak power, drawing peak power from the PV source. So alter R0 to 70. Now let us run. The simulation will run for some time. I will come back after some time. The simulation is about to complete. It's completed. So now let me plot VD again here and see what has happened to the duty cycle. So you see that the duty cycle voltage given to the PWM block, now it has settled to a slightly lower value. It is settled to around 0.5. And if you look at the plot of VT into current through the PV source, the power, it is still hovering around the 26 watt level. There are these disturbances here which should get adjusted if you tune the filters properly. So you see that the hill climbing algorithm we have implemented. The next step would be for you to practically implement them in hardware and try to validate the theory that we have understood and simulated. I will now leave it to you for you to explore the circuit in NgSpice and try to gain more insight into maximum power point tracking.